Okay, thank you all. Thank you very much for a very nice introduction, and many thanks to the organizers for the invitation. So this talk is on the convexity and the concavity of trace functionals. So let's start with a few operations which preserve the concavity. So for example, if you it's very easy to check that the concavity of trace functionals is stable under taking linear combinations with positive coefficients and taking limits and also taking infimum. And sometimes with additional conditions, you can prove that the concavity is also stable under taking supremum. So the point is, if we are given the concavity or the convexity of certain functionals, which might be very easy. For example, in this talk are the concavity convexity result of Lieb and Ando, as indicated from the title. Then one can try to prove the concavity or convexity of more general functionals. For example, for functionals which admit very nice integral formula. But in this talk, we actually will see that this infimum and supremum operations can also be very helpful. So as a warm-up, let me give you two very easy exercises. So the first exercise is to decide for which p x to the power p is convex or concave. And certainly this is very easy. You can compute the second derivative of f. And for a two-variable function, x to the power p and y to the power q, then this second exercise asks for which pairs PQ we have the joint convexity or joint concavity. But this time again is very easy. You can compute the Heisenberg of this function. But it becomes much more complicated when it comes to the noncommutative setting. So let's fix an invertible matrix K and suppose that A and B are any positive definite matrices. Then the following exercise, exercise 1 prime, is a noncommutative analog of exercise 1, which asks for which pairs PS this trace function is convex or concave for any invertible matrix K. But this time you can still compute the second derivative of some functions like this, but it will be very complicated. It becomes rather complicated for the following exercise 2 prime, which is a noncommutative analog of exercise 2. And this family of trace functionals are the main focus of this talk. So you can remember a little bit. This is a parameter. This is a function psi PQS defined in this way. So the aim of this talk is to explain why we are interested in the exercise 1 prime and 2 prime, and also explain how to solve them using the infimum and supremum approach. And for this, we will need a few notations in the following. We will always assume that H is a finite dimensional Hilbert space, and we will need a few classes of matrices. So B of H will denote all the matrices of over H, and we will also need invertible matrices, positive definite matrices, and sometimes the set of all the quantum states. But one should remark that we always assume that a matrix is invertible for simplicity. Okay, so the plan is as follows. The main body consists of 3 conjectures, which are actually theorems. And if there is additional time, I will give a few remarks and questions. So the first conjecture is our starting point, is a conjecture by Wigner-Yanase-Dyson in 1963, which says for any p between 0 and 1, and for any self-adjoint matrix K, the following quantity, which we call maybe the minus skew information, is concave in rho. So actually, we are asking whether this trace function, is a concave function in rho for any K. And this was resolved by Lieb in a very famous paper in 73 by proving, among many others, that the following concavity result. Now we call this result Lieb's concavity theorem. And this theorem tells us that whenever P and Q are between 0 and 1, such that P plus Q is smaller than or equal to 1, then this function, using our previous notation, is psi PQS with S being 1 is jointly concave. And after this, there are plenty of work on the joint convexity, joint concavity of trace functionals, which I can hardly recall most of them, but there is only one result that I need to recall here, which will be used in the following, is the following convexity result of Ando. So this can be considered as a complementary of Lieb's concavity theorem, which says that for P between 1 and 2 and Q between -1 and 0, such that P minus Q is bigger than or equal to 1, then this function is jointly convex. Okay, so that's all that I want to say about the first conjecture. And the second conjecture is comes from quantum information theory when investigating the so-called data processing inequality for the following family of relative entropies. So the alpha Z Rényi relative entropies were introduced by Audenaert-Datta, which are defined as follows. They are quantum generalizations of the classical alpha Rényi relative entropies. And in particular, if you choose Z to be 1, then you recover the so-called quantum alpha Rényi relative entropy. And if you take Z to be alpha, then we have the so-called sandwich alpha Rényi relative entropy. And certainly when alpha tends to 1, both the alpha and the alpha theta converge to the Euro omega G quantum relative entropy. So this is indeed a very large family of quantum relative entropies. And here is a very nice picture by Philip establishing the connection of among many entropy quantities in quantum information theory. And the property that we are interested in is so-called monotonicity, or the data processing inequality for the alpha Z. So the basic question is, for which alpha and Z we have the following data processing inequality. So this inequality says that for any quantum states, rho and sigma, and for any quantum channel, the alpha Z relative entropy of rho with respect to sigma cannot increase under the actions of all the quantum channels. And it turns out that using a standard argument, one can show that this is essentially equivalent to the joint convexity and the joint concavity of the trace functionals inside the definition of the alpha Z. So namely, if we set psi as follows, then we can show that the alpha Z satisfy data processing inequality if and only if as alpha is smaller than 1 and psi is jointly concave, or alpha is bigger than 1 and psi is jointly convex. So this explains us why we are interested in the exercise 2 prime, because psi here is just a special case of psi PQS by taking K to be identity and S to be 1 over P plus Q. Okay, so this picture summarizes the known results of data processing inequality for the alpha Z before our work. So namely, in the orange part, we know that the DPI holds with a knowledge of convexity and concavity results. And in this yellow part, we don't know if the data processing inequality holds or not. And for the other region, we know that it fails. So the question is, in the yellow part, whether the data processing inequality holds is true or not, or equivalently, whether some convexity or concavity is satisfied or not. And this is actually our second conjecture by Audenaert-Datta. So for some P and some Q, whether these families of trace functionals psi PQ, 1 over P plus Q, is jointly convex or not. And so this so now let me move to the third conjecture and present you the solution of exercise 2 prime. Before going to this conjecture, let me first show you what the solution of exercise 2 prime looks like, which is our main result. So namely, we prove that we give necessary and sufficient conditions for the parameter PQS such that psi PQS is jointly convex or jointly concave. This is summarized in the next picture. Before that, let me comment that we can assume S to be positive. Otherwise, you can replace PQS with minus P minus Q and a minus S. So this is our main result. To understand this picture, let's have a look at this green region, for example. So suppose that P and Q are between 0 and 1, and S is between 0 and 1 over P plus Q. Then the corresponding trace function psi PQS is jointly concave, and otherwise it is not jointly concave. And similarly, if the triple PQS lies in this yellow region or this orange region, we know that it is convex. Otherwise, it is not. So this is a very nice picture, but actually it takes quite a long time to complete this picture. On the necessary part, so it was Rényi who proved that these conditions are actually necessary. And this was done by testing some very special 4x4 matrices. And the first significant sufficient result might be the Lieb's concavity theorem that we mentioned. And in the following, we will complete the whole sufficient picture using the following very fundamental result, the following building blocks. So the first building block is a particular case of Lieb's concavity theorem, namely psi P1 minus P1 is jointly concave whenever P is between 0 and 1. So the second building block is a special case of Andon's convexity result. So the same function is jointly convex when P is between -1 and 0. Actually, we need one more fact, which is kindly well known, saying that for any positive t, the function trace of a to the power minus t is convex. So actually, you can replace the function x to the power minus t with arbitrary convex functions fx. So for simplicity, let me name it building block 3. And these are essentially what we need in the following. So this is a very brief history of important progress on proving the conditions to be sufficient. So, so certainly many people's names are missing here, so I feel very sorry about that. The point is you can observe that the green part and the orange part are very nice because compared with the previous picture, we know that the green part and the orange part, the conditions are necessary and sufficient. And the problem lies in this yellow part because from the necessary condition, it suggests that the convexity here should be true whenever S is bigger than or equal to 1 over P plus Q. And this is actually our last conjecture, the conjecture by Carlen-Frank-Lieb, saying that in this part, the convexity should be true whenever S is bigger than or equal to 1 over P plus Q. You can easily see that the AD conjecture is just a special case of CFL conjecture by taking S to be 1 over P plus Q. And we will confirm these two conjectures, and therefore the picture is complete. Okay. As I said, we will complete this picture. So the proof, we prove that in the yellow part, the convexity is true whenever S is bigger than or equal to 1 over P plus Q. And the proof is actually very easy. But more surprisingly is the same proof actually applies to the green part and orange part. And the strategy of this proof can be seen from this picture in a very naive way. So the point is we want to reduce the problem on the green part, yellow part, and orange part to the result on the red line. So the red line are just two red lines, are just two intervals. Actually, one interval because of the symmetry. So the red part is just the interval -1 to 2. And our strategy is as follows. We want to find the argument which allows us to reduce the problem of this green point G to the red points G1 and G2. So we want to find the argument such that the joint concavity of some function green point G here can be deduced from the concavity of functions red G1 and red G2. If there is such an argument, then very likely similar argument will work for the not only for the green part, but also for this yellow part and this orange part. And this sounds a little stupid and incredible, but actually it works. We can find such an argument to realize this reduction method. But to explain this argument, let me first give you another proof of exercise 2, the scalar setting. We know that, so in the following, we will prove that when alpha and beta are between 0 and 1, such that alpha plus 1 is smaller than or equal to 1, this scalar function psi, alpha beta is jointly concave. Certainly we know that this can be done easily by computing the height of this function. But in the following, we will give a variational proof. The idea is that the concavity is stable and taking minimum. So namely, if you have a family of concave function, then their minimum, whenever it exists, is also concave. Therefore, the desired joint concavity of psi alpha beta will follow from the following variational formula, together with the concavity of this one variable function, t to the power alpha plus beta. Why is it so? Because we know that from this one variable concavity result, that this part is concave in X and this part is concave in Y. Therefore, their convex combinations is jointly concave in X and Y. And after taking minimum, we know that the joint concavity is preserved. So this finishes the proof. And the proof of this variational formula, which is a key, is actually very easy, right? You can do this by computing the derivative of this function as a function of z to check this minimum. But this proof doesn't tell you what to prove in the noncommutative setting, which is more important. So in this talk, all the proofs are easy, but the point is you need to figure out what to prove. So let me present you another proof of this variational formula. So suppose that P and Q are positive numbers such that their inverses sum up to 1, then we have this Young's inequality or Holder's inequality. Now, if I replace AB with a pair AC, C inverse B, for arbitrary positive C, then this inequality, the left-hand side is the same, but the right-hand side is a function of C. Now, it's very easy to find the positive C to capture the equality, so that we have a variational formula for the product AB. And this will give you the desired variational formula immediately. So this argument is more heuristic because the crucial point is nothing but the Holder's inequality and Young's inequality, certainly. And we know that this is true for Schatten P norms. Schatten P norms have Holder's inequality. So we have this variational method for the matrices, namely for X and Y. Say X and Y are invertible matrices, and Ri's are positive numbers such that you can apply Holder's inequality. Then you have this minimum formula and maximum formula. And they managed to separate the variable X and Y successfully, as you can see. A few remarks are as following. So firstly, these formulas are certainly not completely new. Special cases were known and have been used to prove the joint convexity and the joint concavity of trees functionals. I think this is possibly first applied by Carlen-Frank-Lieb for this maximum formula. When this part becomes linear, then it is actually a noncommutative analog, noncommutative counterpart of the Lambda transformation. So another remark is that the minimizers and the maximizers Z here are not unique in general, but Z times Z star is unique. And this is helpful when studying the equality conditions. Okay, now we are ready to solve the exercise 1' and 2'. So for the exercise 1', it actually corresponds to the red line. On the red line, we know that either P equals 0 or Q equals 0. Therefore, the two variable functionals psi PQS becomes a one variable trace functional. Therefore, this is actually the solution of exercise 1', and this is actually already known due to the work of many people, Epstein, Carlen-Lieb, and Rényi. So you don't really need to read in details of this statement. It just tells you that on the red line we have all the desired convexity and concavity property. Now let me explain how this reduction argument works. How can we reduce a problem of green region to the red line? So we want to prove that in the green region, the function psi PQS is jointly concave. Okay. If P equals 0 or Q equals 0, and then it is just reduced to the problem of red line, which is known. If not, then we can apply our variational formula to write psi PQS as minimum of some functions which are simpler. Namely, you can identify this psi PQS as a green point G, and then this the trace functional inside the brace. This we denote by G1. This you can understood as the red point G2. They are both concave due to the result on the red line. And then from our first idea that the concavity is preserved under taking minimum, we know that this function G is jointly concave. And this finished the proof of the green region. And the proof for the yellow region and orange regions are similar. You use a maximum formula instead. Okay, so now we use our first idea to reduce the problem of exercise 2' to exercise 1'. But the classical proof of red line of the exercise at 1' is actually not very easy. In particular, you will need the so-called analytic method by Epstein. So here I want to give a simpler proof. This is based on the following second idea. So the point is, in the first idea, we use the fact that concavity is preserved, is stable under taking minimum. But sometimes we have very nice maximum formula, and we want to prove the concavity. So the second idea tells you that whenever of two variable function f is jointly concave, then the maximum over the second variable is concave. as a function of the first variable. So with additional conditions, we can prove the concavity using maximum formulas. For example, whenever p is between 0 and 1, we have this variational formula, this maximum formula. Then this one variable function as a function of a, its concavity will follow from the joint concavity of the function inside the brace. And this part is linear, so essentially the concavity of this function, of this one variable function, will follow from the joint concavity of this function, of this two variable function, which is nothing but the building block 1, the concavity result of Lieb. And this is not a coincidence. So in general, for example, in the green region, the joint concavity of this psi PQS after a chain of minimum maximum formulas can be deduced from the joint concavity of this function, which is our building block 1. So this is a concavity result of Lieb. And similarly, in the yellow region, the joint convexity of this psi PQS after chain of maximum and minimum formulas can be deduced from the joint convexity of this function, which is our building block 2, the convexity result of Ando. And orange part is slightly different. The joint convexity of psi PQS will follow from building block 2 and building block 3. So we need one more fact about the convexity of trace a to the power minus t in general. So to conclude, we with our variational formulas and ideas 1 and 2, to obtain the whole picture, essentially we need only the building block 1 and building block 2. So essentially, we only need the joint convexity and joint concavity of these special trace functionals, which appears in the conjecture by Wigner-Yanase-Dyson. I will not discuss the proof of this result of Lieb and Ando, because now we have plenty of proofs of this fundamental result. So to conclude, we start from the conjecture by Wigner-Yanase-Dyson, and we have the concavity result of Lieb and Ando's convexity result of these trace functionals appearing in this conjecture. Then using our first and second idea and our variational method, we can solve the exercise 1' and 2'. And finally, we complete the whole picture. And in particular, we resolve the conjectures by Audenaert-Datta and Carlen-Frank-Lieb. So this is the whole story. Okay, I still have a few minutes, so let me end with a few remarks and questions. The first remark is on another concavity result of Lieb in his famous 73 paper. So in this paper, he also proved the following concavity result. So here, K is arbitrary fixed self-adjoint matrix. Then Lieb proved that this function f is concave in A. If we use the Lieb product formula, we can write this exponential as a limit of something which looks nicer, and therefore this function f can be written as a limit of some functions, which is of the form in the exercise 1'. So if you apply the maximum variational method again, then this function f is actually a limit of some maximum of some functions. And here, these functions are just as the trace functions appearing in the conjecture of Wigner-Yanase-Dyson. So therefore, the joint concavity of result of Lieb, namely the joint concavity of this trace function, will imply the concavity of this function f. So this is not surprising. If you just formally exchange this limit and this maximum, then there is another variational formula for this function f, where this f can be written as a maximum of some function which is given in terms of the quantum relative entropy. So that duality formula is also kind of well known. So this is the first remark. The second remark is on the equality conditions. So essentially, we prove the data processing equality for d alpha z based on the following two variational formulas. For PQ between 0 and 1, we have this minimax formula for the trace functionals inside the alpha z Rényi relative entropy, and for P between 1 and 2 and Q between -1 and 0, we have these max minimum formulas. So if you are looking for some other properties which are stable under taking these minimax formulas, and this such formulas possibly will reduce your problem by looking at these simpler trace functionals. So the point here is that the corresponding minimizers and maximizers in these variational formulas are all unique. Therefore, we can use this to give some algebraic equality conditions of data processing equality, which I will not go to details here. So the first question is still on these equality conditions. So in general, I think it's we have some partial results on the equality conditions of data processing of DPI of d alpha z. For some of them, we can show that the equality will imply the existence of recovery maps. But I think in general, for general alpha z, such that DPI holds, I think is still largely open. The second question, the last question is, now we know very well about the convexity or the concavity of these trace functionals as a function of A and B. But how much do we know about the convexity or concavity of this function as a function of K? So in general, you can certainly put some power R here. And here the powers of A and B are certainly they don't matter in general. So maybe this is just my lack of knowledge, so I don't know. Certainly there are some partial results, but I don't know the convexity and concavity of these trace functionals for general AB in full generality. So these are my last question, and that's all that I want to say. Thank you very much.